Good morning, everybody. Today we're going to finish up our notes on describing physical phenomenon. So today we're going to look at varieties of velocity. Oops, there's that letter again, V and V. Oh, that's because these are vectors. So varieties of velocity. And some of this is going to sound vaguely familiar, except there is a big difference between speed and velocity. You should know what that is by now. All right, the first thing we're going to talk about is constant velocity. This means that the magnitude and the direction of the velocity stays the same, and it is a rate. All right, it's a rate of change in position or rate of displacement, because change in position and displacement are the same thing. So you could write it as change in position, which is a vector quantity, and put our little vector symbols on there, and time in the denominator, because that makes it a rate. Or we also could say that the constant velocity is the rate of displacement, since delta x and d are the same. Very much like speed, the units come from what's in the formula. Displacement is measured in meters. We're dividing by time, which is measured in seconds, so we get meters per second, which is considered to be a derived unit. Now, if we rewrite the formula very much the same way we did with speed, we get a linear form, y equals mx, with an understood plus b of 0. So this is a linear form. So if we plot the position on the x-axis and the time on the y-axis, say backwards. If we put the position on the y-axis and the time on the x-axis, then the slope of the graph would be the velocity. Only this time, because these are vectors, we can look at direction as well. So the sign of the slope is going to be the direction of the velocity. So this is a positively directed velocity, and it is constant because it's a constant slope. If it's a straight line, I'm riding on top of one of those foamy table mats, so it's not very straight. You can make yours straight though. All right, positive slope, positively directed velocity. But you could also have a negative slope. And if you have a negative slope, then you have a negatively directed velocity that's constant. All right, so here, these are the directions. Sign of the slope is positive, the direction's positive. Sign of the slope is negative, the direction's negative. The numerical value of the slope is the magnitude of the velocity, okay? So we're going to write that right here, okay? The sign of the slope is the direction of the velocity. And the magnitude of the slope is the magnitude, that is the numerical value, of the velocity. Did I go off the edge there? Oh, almost, not quite. There you go. So it's very important that you know both of those specific things about the slope of a position time graph, because these are vector quantities, so direction makes a difference here. Okay, now what if the velocity is not constant? Because like it or not, that's the way life is. It's not going to always be constant. Well, very much like what we did with average speed, we can do the same and talk about average velocity. Okay, so if you talk about driving west on Manatee Avenue towards the island, you could find your average velocity by either adding up every velocity of every second that you take to travel out there and dividing by the number of velocities to get the average, Or you could find the average velocity by taking the total displacement you travel from where you start to where you end up and divide it by the total time. But now remember, that's going to have a direction with it, okay? Now, at the moment, it's probably occurring to you that this looks just exactly like what it did with average speed. But now we're going to do some little examples that are going to show you it's nothing like average speed. So let's take a look. Suppose you have a hiker that starts from camp. All right, so that dot represents camp. And this hiker walks 2 kilometers north in 2 hours. North being up the paper. And good question. In case you're not sure, let me draw a little compass rose. On our paper, standard convention, north, south, east, and west. Okay? That's a standard compass rose. That's how we tell direction from cardinal directions on our paper. Okay? All right, so north it is right here. He goes 2 kilometers north. Then he turns and walks 2 kilometers east in only 1 hour. Oh, and I forgot to put 2 hours right there so we know. So he turns and he walks 2 kilometers east, but it takes 1 hour. Okay, he was in a hurry. Then he turns and again and walks 2 kilometers south in 2 hours. Oh, I forgot the E for east right there. And then he's going to turn one last time and walk 2 kilometers west. And he does it in 1 hour. He's hungry. He wants to eat dinner. Okay, so this is our trip that we've made. Now we're going to analyze this trip 2 ways. We're going to analyze it using scalars first, then using vector quantities so that you can see the difference. All right, now let's first find the total distance traveled and the total time. Okay, there goes my clock, sorry. All right, if we were to sum the distances, okay, and let me show you right here, the Greek letter sigma is shorthand for summate. Just like the Greek letter delta is shorthand for subtract or differentiate, okay? So if we sum the distances, we're going to get 2 plus 2 plus 2 plus 2. Oh, that's 8 kilometers that the person actually physically walked. That's the path length, the distance traveled in that time. And what is the total time for the trip? Well, that's easy. 2 hours, 3 hours, 5 hours, 6 hours. So this person walked a distance of 8 kilometers in 6 hours. That sounds reasonable, doesn't it? All right, let's go to the next page for a minute. So now we want to determine what is the hiker's average speed for the hike. Well, average speed is found by taking the total distance and divide it by the total time. So that's going to be 8 kilometers over 6 hours. And let's see if you divide, I think you get, is it 1.6? Let me just make doubly sure here, guys. I want to make sure I write it down correctly for you all. All right, so my calculator, now I have to find my calculator. I got too much stuff on my phone. All right, so we get 8 divided by 6. Yeah, oh, yes, not 1.67, it's 1.3 repeating. So 1.3 repeating, and that's going to be kilometers per hour, because that's what we have right there. So there's the average speed for the trip, and that makes perfect sense. If you walk 8 kilometers in 6 hours, you're going to average around 1 1/3 kilometer each hour you've traveled. Now, let's describe the same trip using our vector quantities. So first, we want to find the total displacement traveled. Now, the total displacement, here's where you have to remember, the displacement is the difference or how far you are on a straight line between where you started and where you ended up. Well, where did the hiker start? Oh, camp. Where did the hiker end up? Oh, camp. What's the difference between those two positions? 0. Okay? And a total time still of 6 hours. So if we want to find the average velocity for the trip, we're going to take the total displacement, divide by the total time. I think you can see 0 divided by 6 is going to give us 0 kilometers per hour. Big difference, isn't it? But that's because distance and displacement are very different. This is the path length traveled. This is how far you are from where you started on a straight line. Two completely different descriptions, both valid, but different. Okay? All right. Now, the last type of velocity I want to look at is instantaneous velocity. Yes, it sounds just like instantaneous speed. It is your velocity, both magnitude and direction, at a point in time, a single point in time. And yes, you can find it on a graph too, just like you can average velocity and constant velocity. It's the slope at that point in time. However, one thing I would like to talk about for a minute. If you're in your car and you look at your speedometer, does it give you your instantaneous velocity? Well, think of the name of the instrument. It is a speedometer. It gives you your speed, not your velocity, because the speedometer can only give you the magnitude. It cannot give you the direction part. So, no, a speedometer does not give you your instantaneous velocity the way it gives you your instantaneous speed. If you wanted to get your instantaneous velocity, you would also need a compass. The speedometer would give you the magnitude, the compass, the direction. Okay? All right, let's take a look at some common position time graphs. Now remember, the slope of a position time graph is always going to represent the velocity. The magnitude of the slope is the magnitude of the velocity. Remember, magnitude is just a fancy word for numerical value. The sign of the slope, positive or negative, represents the direction. So that means on a graph, we can only show two directions, either positive or negative. We cannot show north, south, east, west. We cannot show up or down, left or right. All we can show is positive or negative. Okay? Let's talk about an object at rest. Now, because we have directions, we can do this. We can have positive positions. We can have negative positions. Can you have an object at rest at a positive location? Sure you can. Whatever that positive location is, it stays the same for the time period in question. You don't change position, you're at rest. Can you have a negative position? Certainly. And it would stay constant for the time period in question. All right, now let's look at an object traveling at constant velocity. Okay, if you have an object traveling at constant velocity, remember, we can have more than one direction. So, you could be traveling at constant velocity in the positive direction. So here, it's a constant slope, so it's a constant velocity in the positive direction because the sign of the slope is positive. Can you have an object moving in the negative direction at constant velocity? Certainly. You just have a negative slope. So this would represent a constant velocity in the negative direction. Okay? Actually, I probably should have put that one over there, but oh well, c'est la vie. Now, let's talk about an object with changing velocity. Oh boy, this one's going to get a little tougher, and we are going to need both sets of axes on this one, no doubt about it. So I'm going to put a positive position right there, negative positions there, positive here, negative here, and of course, the x-axis represents the time. Now, let's first look at how objects can increase velocity, and that would be the numerical value. So that means you would have increasing slope values for increasing velocities, and you can do it in two directions. You can do it in the positive direction, you can do it in the negative direction. Okay, so let's see what an increasing velocity in the positive direction would look like. Okay, so here we have increasing positively directed velocity. The slope is getting more vertical, it's getting steeper, so that's increasing magnitude, and it's in the positive direction because it's still a positive slope. Can you have increasing velocity in the negative direction? Certainly. You just have to remember it's got to get steeper. It's got to go from horizontal to vertical. So that might look something like this. It's going from flatter to more vertical. So here you have a slope that represents increasing velocity in the negative direction, increasing negatively directed velocity. Okay? So both of these show increasing velocity in two different directions. Now let's look at decreasing velocity. Because we can do that in both directions also. It's just we have to remember to decrease the velocity means we decrease the slope. We have to go from vertical to flatter. Okay? So decreasing velocity in the positive direction, that would look like this. You start out steeper, you get flatter. Okay? So here we have a slope that shows decreasing positively directed velocity. Can you show an object slowing down in the negative direction? Certainly, you're going to do the same thing. You're going to start out steeper and get flatter. So this shows decreasing negatively directed velocity. Okay? All right, so increasing, the slope goes from flatter to steeper. Decreasing, the slope goes from steeper to flatter. And up the graph is the positive, down the graph is negative. Okay? I hope you've enjoyed this. It's been a lot of fun doing graphs, and now we're going to be able to do some fun little activities I've got prepared for you. Have fun. Bye-bye.